Hi everyone, today I want to explain what is Heegaard splitting and length space very intuitively, so that if you don't have adequate background knowledge, you can still understand. And I'll try to do my best to achieve that goal. So basically, in order to do that, I need to make sure you understand what is a manifold, what is a two-dimensional manifold, what it's S2, and all those terminologies. So I'll start from the very basic. So we know that. So basically, we have all these notations that I'm gonna go through one by one. So S1, it's just this circle that's hollow. Basically, you can imagine you have a string and you just tie. So you have two strings, right? And then you identify this point with that point and this point with that point. So then, basically, two strings hugging this disk sort of space. But S1 is just the strings. So it's just like this string, and it's constructed by gluing two intervals along their boundary. So the boundaries of interval is these 2 points, right? Okay. So S2 is so the number here denotes the dimension. So S2 is 1 dimension higher. So that you can imagine what it's like. But just give you the answer. It's this sphere. Imagine a soccer ball, except that it's not filled in. So S2 is just the shell of it. So it's constructed using you have two discs, right? So this is one disc, this is another disc. They're this more circular, and then the boundary of a disc is just this S1, right? So this circle, and then you glue the boundaries of them together. So then basically you have two discs, they're hugging this spherical space, and then that's S2. And S3, so you see how interval disc. So actually S3 is constructed using 3 balls. So this time it's filled in S2, which is called ball 3. So the gluing, the way we said it, you glue two things together along the boundary. We actually denote it this way. So we use this notation, right? And then this is the boundary of the interval, right? And this is glued by the boundary of S1. And I guess here I need a little bit more space, which I will redraw. All right. So these two, so S3 is constructed where you glue two ball 3. So each of these is called 3 ball, because you wanna have something to denote to differentiate this from this, right? Because this is filled in and that's just a hollow shell. So when you glue them together, you're actually gluing together along the boundary of S2, because the outside boundary of a ball is just the shell of it, right? And exactly how do you do this? How do you take two solid ball and then glue them together where you identify each point the boundary? Actually, that's very hard to imagine, right? That's exactly because of this following fact. So S3 actually lies in R4 or C2. So why is that? So you can see here, even though the circle, it's kind of if you just stand on this circle, you walk around, right? You can only walk in this singular direction that's constructed by the circle. So locally, you feel it's kind of one-dimensional. But in order to visualize the entire space, since it's hugging, since it's two interval where it's hugging, it's constructed by gluing them together. So there's hugging some sort of hollow space in between. So because of that, you're actually by this gluing kind of method, you're actually creating another dimension. So in order to visualize the whole space, the whole S1, not just two intervals but the glued together version, you actually need to see it embedded in a plane, kind of the blackboard. So you can see this. And so is S2, right? We can easily visualize S2 because we think of it as the shell of a ball, right? And we're living in a three-dimensional world, so it's very easy for us to imagine what a soccer ball looks like and the shell of it. But you see how if you're just walking on this hollow shell, like locally, you're just like walking around, right? And if you're very, very small, if you're very, very small compared to the space, so like you zoom in really closely, actually things look really flat. Like so kind of like the analogy here, where if you walk around, you kind of like, if you're very, very small, you're walking just like straight forward. But if you're very, very small here, right, you take a small patch of the, so if you're like here, right, you take a small patch, and then it's very, very small. If you're very, very small, kind of like us humans on Earth, right? We were walking around, Earth is spherical, right? But for us, like everything is really flat. So that's kind of like S2, where like disks are flat, but when you glue them together, right, you're embedding this like space, and that means you have to like, in order to visualize the whole S2, you have to like see it in the three-dimensional like setting space. So you see S2, you can visualize S2 in our like three-dimensional world, right? Three-dimensional space. So here we have S3. So since the space itself is three-dimensional, and you know, we're actually gluing together two three-dimensional like filled in like ball. Like that means like you know, these two are three-dimensional. The gluing, the process of gluing, actually, because it's hugging some sort of space, you're identifying this along the boundary of the ball 3. So like 3 ball. So this process of like gluing actually adds one dimension, because like you're hugging some sort of space, right? So in order to visualize S3, you have to like see it in the 4th-dimensional world, and that because we're living in a 3-dimensional world, and our mind just cannot imagine what it's like. So of course you cannot understand what S3. So here, I hope you are following so far. And then I'm gonna go into what is a Heegaard splitting. So Heegaard splitting is kind of a way to visualize like how a three-dimensional manifold are constructed, and I think a very simple example would be like Heegaard splitting of S3. So actually, I don't think I'm pronouncing Heegaard correctly, but okay. Let's focus on what I was going to say. So Heegaard splitting, like the name is like Heegaard, it's like the mathematician, and splitting is like, you know, you're splitting the space into like two. And as you can see, kind of like in the sequence, we kind of like always have like, if it's like a three-dimensional thing, we need to like have two other like two-dimensional surface, and we're like gluing together along the boundary, and then that gives us a three-dimensional three-dimensional like, so what I'm trying to say is like the boundary of the two things we're gluing together has to be two-dimensional, and then when we hug them, right, when we hug the space, the entire thing becomes three-dimensional, and one Heegaard splitting, so like S3 can be constructed by this way, right, but it could be constructed other ways. For example, you know, just like how S2 could be constructed this way, we can also construct in other ways. So S3 could be constructed as you know, a solid tori glued along the boundary of T2. So okay, so this is a torus. But it's filled in. So imagine kind of like a donut, except like it's like filled in, so it's not just like I guess donuts are filled in. Like, okay, but then normally when like topologists say like a torus, they mean like the shell of a donut. So when people say like T2, can you still see? Yes. So when people say T2, they normally mean just like, you know, the shell of a donut. So like this hollow thing that kind of like has like kind of like hollow tube thingy. It's funny because like I actually said hollow tube thingy, and okay, in my research meeting, and I think it's fun. And so like filled in torus, so S3 can be constructed by two filled in torus glued along the boundary of T2. So I'll just like draw another filled in torus here. Right. Okay, so I feel like this is kind of hard to like imagine, like how you do it. So like I want to try to like help you like maximally like visualize this process. Actually, can you see? Oh yeah, I think it's pretty clear. Okay, so I have some space on this side. All right, so how exactly does this work, right? So you have two donuts, right? They're literally donuts. They're filled in, right? But they're kind of like perfect donuts. If you zoom in, like it's kind of like imperfect. The surface is kind of like not very smooth. But like imagine this comes to like a very perfect donut, right, and basically these two donuts are identical. So that when you so that the boundary of one is exactly like 1-to-1 with the boundary of the other, meaning like every point here you can find one and only one unique point here, and you say they are the same. Kind of like in this example, you say this point, which is the boundary of an interval, right? Interval is like this, so the boundaries are the top and the bottom. So the top point and the bottom point, so you're trying to say like the top point of one interval is exactly the same as the point here. So basically after you glue them, it's as if like you're walking in this interval, and when you get here, you're also like you're also simultaneously here, because like these two are the same point in space, just like represented differently. So you can, it's kind of like, you know, kind of like teleportation sort of, except that it's not really, because like these 2 points are the same points. And basically in this case, right, you want to do something similar where you say every point on this filled-in torus, it's actually okay. So I'm trying to say, so the boundary kind of like it's the boundary is like identified. So the boundary of the filled-in torus is identified with the boundary of this filled-in torus 1-to-1. So kind of like this example where like, you know, sorry, actually I'm not gonna draw like exactly how they're identified, because like they're identified in a way that's kind of hard to imagine. But okay, so I'm gonna try to explain how they're identified in the following attempt. So before I do that, I want to talk about like how do you do this? Like, so you see in this example, right? The boundary kind of like they're kind of symmetrical, in a sense. So like how exactly is like this T2, like the boundary of T2, like I guess like the T2 itself, how exactly is like how exactly do you like do 2 copies of it? So okay, so here's the thing, right? You take a T2. Actually, I think if you're interested, you can look up like Wikipedia, Clifford torus, CLIFFORD torus, and then there's like really cool visualization. But I'm gonna try to explain like hand wavily the intuition. Like so basically, you take this like torus, right? It's like this torus, like T2, like just like a hollow shell. It's the boundary, how they're glued, right? Because like you know, you're taking like all the points on the outside and all the points outside here, and then you're gluing them. So you kind of like take this part and you just like fatten it, right? You just like make it like really really big. So then it kind of like becomes all right, so becomes like this. Right, you see how like this is the original donut, and then you just like make it really big, so it like becomes like this is the original donut, and then you kind of make it bigger and bigger, and eventually it becomes like kind of like this thing where it's and this is my best attempt at like trying to draw it. So basically, so forget about the pink curve at the moment. You just take the purple one, and you just kind of like fatten it a lot, and then eventually, imagine it just like blows up, and this this purple kind of like goes around, and then originally it's like part of the donut becomes like part of the whole. And this like flipping, it's exactly like the two sides of the so you see how like after we flip it, right, we're like this pink, it's literally just like another torus, right? Just like that, right? So you see how like we started with a flat torus, and then after we flip it, it becomes like a vertical torus. So and then both space have the same boundary, right? The boundaries are both T2, and so basically you can imagine you bound one solid torus in this, and then you bound another solid torus here, right? And then they're glued together by this T2. And so another way to visualize this would be, you know, you take one solid torus, and then you put kind of like another torus. So I guess like the canonical way to demonstrate this is like you draw a circle on the torus, and then you draw another circle on this torus, except it's like this vertical circle, and you glue them together such that, you know, this circle identifies with this circle. Or I guess like a way to like visualize this would be like you put another torus kind of like this here, except that, so like I guess right, so I guess like so you can like this, and then you can't really see this part because it's like kind of blocked. Okay, so it's kind of like that. You see how like, and the surface that they're except that, you know, it's not just this, this is kind of one way to like understand it, but it's not quite that, because like you see how here they're just glued together in this patch, but you imagine like this kind of goes around, and then this whole thing that after like it's every point on the surface is identified, the boundary where they touch, it's a T2, the boundary of it's a T2, and the whole thing is like a compact space that we call S3. All right, I'll stop here for now. I didn't know if I promised I was going to talk about lens space, but I don't think I'm going to do that. Hopefully you understood. Hopefully you enjoyed it. Thank you.